Okay, gang, Math 5500 again. We're moving into quadratic regression using least squares. And the motivation here is, as you can see with the plot on the left, sometimes we get a relationship that's well modeled by a linear function and creates a smiley face. And sometimes we get a relationship that clearly would be better fit by another model. In other words, if you try to use the linear model, not good. So anyway, we start out with the same setting. We have a set of data, and I think you're going to find that the transition from linear models into quadratic models using least squares approach is a smooth transition if you have just again, the general overview of the process. Establish Q, take the derivative, could be the partial derivatives, and set it equal to 0 and solve. We don't get into the second derivative to verify that it is a minimum. Maybe should, but I think all of you are capable of doing that if I ask you to do that. So the form we have, again, establish Q. The only difference here, we're looking at the general form, where we're not looking at just the b0 plus b1 x sub I, but we have additional terms, where k is the degree of the polynomial. The focus of this video is to take a look when k is equal to 2. So take a look at quadratic regression using the least squares approach. All right. The thing I will tell you, again, in an attempt to make the videos shorter, I think my video when I created this course on quadratic regression was like pulling teeth. It was just way too long, and because the calculations are really tedious. So, I'm going to fast forward through some of that. I'm going to show you what the calculations lead to, but I'm not going to sit there and or sit here and perform those calculations. All right, so we got data. We'll look at an example. 4 data points. Just an aside, when k is equal to the degree, in this case we're looking at degree equal 2, there will be k plus 1 partial derivatives. So the reason is we have b1 and b2, and of course the intercept. So gang, again, in establishing the Q, we enter our data. So in the first data point, we have x is 0. So we put 0 in both places for x. This is the y. Here's our x for the second data point. Here's our y, and so on. Next thing we do is we look at the partial with respect to b0. So if I look at the first term, I'm going to have a 2 times this expression times the derivative of the inside part with respect to b0, which will be a -1. So we get -2 times 2.1 minus b0. The reason the b1 and b2 terms go away is because our x value is equal to 0. You can see that that's not the case for the other terms. So when we simplify that, we get -101.2 plus 8b0 plus 12b1 plus 28b2. Now, I went ahead, and I'm not going to show the calculations for it, but I encourage you to at least run through the partial for b1 or b2, ideally both of them, and make sure that you get this and this. But that's really up to you. It's just really just a whole lot of arithmetic, if I'm going to be completely honest. Next thing we're going to do is we're going to solve simultaneously. So we're going to set up a matrix, 3 by 3 times the beta matrix will equal our coefficient matrix. So we solve that by taking the inverse times the matrix to the right. Now let me show you how we do that in R. Let me jump out of here and bring up R. Actually, there's some work from a previous video. So what I would do here is I would probably just call it mu x for lack of any better term. So I'm going to call, type in the numbers for the first matrix. Taking a little bit more time with this because we're going to be using matrices to do quite a bit later in the class. And let's call this new y because I'm not that creative today. You might say, Dr. Darbo, you're never creative. I probably would agree. Eight. All right, so let's create a x1, we'll call it, matrix. So I want to use new x, and I want in row to be equal to 3, and in column to be equal to 3, and by row equal true. So we see x1 is exactly what we need it to be. Let's establish y1. It's a little bit easier. Matrix, what I call that, new y. In row equal 3, in column equal 1, by row equal true. Just to confirm, we have this. Now, to take the inverse of the x1 matrix, remember we use the solve command. So x1, and then to multiply matrices, we have to do something a little special, and y1. And you can see when we, so we get 2.47 as the B0, so I think I need to correct that. All right. So again, 2.12, 2.47. So this would be our model of best fit for the quadratic function. Now we can, you know, dive a little deeper into this. I guess I want to do, yeah, I'll tell you what, let's do that. Just like we could establish the linear model directly using R, we can also do that for the quadratic, but we use a little different form. So we're going to use the linear model. Now, I'll tell you what, I got to back up. I have to enter the data, so. All right, let me find that. And then my y's are going to be a little tougher to type. All right, is that correct? Yeah. All right, so now we can create our model using the LM function, but we do a little differently than we do with the linear model. So we're going to take y predicted by x, but we're also going to include a term for the x squared term. I'm having a hard time typing, guys. Oh, let's see what happened. I used a cap x. All right, much better. So summary model, again, you can see the coefficient estimates, 2.47, 2.12, and 2.00 that we had before. All right, even get a multiple adjusted r squared. I'm sorry, multiple r squared, adjusted r squared. We would say here that 99.2% of the variance of y is explained by the regression on x using the quadratic model. So, guys, that's all I got. I hope this helps with the quadratic regression part. Take care.